Four corners. Light and shade. Susanna Daniel. Light and shade. Light is vitally important to our planet. Think about how often you use light. Maybe you turn on a light to get dressed, use sunlight to locate your bike outside, or click on a torch to find your socks under the bed. Light is important for reasons other than seeing things. Without light, most living things could not survive. Plants need light to grow. They absorb light and use it to make food. Light from the sun is the main source of heat and other forms of energy on Earth's surface. Sunlight also plays a major role in the changing seasons and the illumination of the moon and planets. Most animals and plants that live underwater need sunlight to survive. Some of our sources of light are natural, such as sunlight. Others are artificial, such as electric lamps. However, all light has the same characteristics. Knowing what these characteristics are can help you predict how light will behave. It can also help you understand the role light plays in shaping the world. The activities in this book can help you understand about light and how it can be manipulated in the creation of optical devices, such as a camera and a periscope. You can also observe the role of the sun's light in shaping the cycles of day and night and the seasons, and in illuminating the moon's surface. Before you begin each activity, gather all the materials you will need. Then use the photographs to help you follow the instructions. If you see this symbol, please ask an adult to help you. Take your time working through each experiment and have fun. An electric lamp produces artificial light. The behavior of light. Light is a form of energy. When we talk about the behavior of light, we are talking about the way in which it travels and how it interacts with matter. For example, light behaves differently when it strikes a transparent object than it does when it strikes an opaque object. It will pass through the transparent object, but it cannot pass through the opaque object. Light can be bent as it passes from air into water or glass, or it can be reflected, bouncing off the object it strikes. The activities in this chapter will show you some of the ways in which light behaves. Directing light. You and a friend can direct light to see how it behaves as it travels. Materials. Scissors. Cardboard. A hole punch. A narrow beam torch. Procedure. 1. Cut 3 identical squares of cardboard. Then use the hole punch to make a hole in the center of each square. 2. Line up the 3 squares so that the light from the torch shines through all 3 holes. You may need a friend to help you hold the squares straight. 3. Move any square to one side or the other. Watch what happens to the light. The sun's rays show how light travels in a straight line. Transparent, translucent, and opaque. These photographs show how light behaves when it hits. Materials that are transparent, translucent, and opaque. The orange arrows represent light rays. 1. The rays go through the transparent material. 2. Some of the light passes through the translucent material, but some bounces off the surface of the material and scatters. 3. Light rays cannot pass through opaque material. Look and discover. What happened when you moved one of the cardboard squares? Cardboard is opaque, and light cannot pass through it. However, light can pass through a hole. When the holes in the cardboard squares were lined up, light from the torch passed through them all. When one of the squares was moved, the light was blocked. This experiment shows that light beams travel in straight lines, called rays. Reflecting light. Sometimes light rays bounce off materials that they encounter. This is called reflection. The angle at which the light hits a reflective surface affects both the way it bounces and how much it bounces. See for yourself how angles affect reflection. Materials. A shallow black pan. Water. A torch. Procedure. 1. Fill the black pan almost to the brim with water. 2. Darken the room. Then turn on the torch and hold it above the water so the light hits the water surface from directly above. 3. Shine the torch at a low angle across the water surface. How reflection works. If you drop a ball straight down, it hits the ground and bounces straight back up. If you throw it at an angle, it bounces away at the same angle. Light rays work in the same way. Light rays are reflected from a surface at the same angle at which they hit the surface. Light from the torch bounces off a mirror. Light is reflected straight back. Look and discover. What happened when you directed the torch beam directly above the surface of the water? Did the water seem very dark? How much light was reflected back into the room? Compare that to what happened when you shone the torch at a low angle. How much light was reflected into the room? Which torch position reflected more light into the room? When light strikes water from directly above, the water seems very dark. The light passes through the surface of the water and falls onto the base of the pan. However, when light hits water at a low angle, some is reflected back into the room. Refracting light. When light rays pass from one transparent substance to another, they change direction. This is called refraction. This activity will help you explore how light refracts. Materials. A cardboard shoebox. A pen. A ruler. Scissors. A sheet of white paper. A glass jar. Water. A torch. Ask an adult to help you with step 2. Procedure. 1. Draw 2 vertical lines, about 2.5 centimeters apart, down the middle of one short end of the shoebox. 2. Cut narrow slits along both lines with the scissors, leaving at least 2.5 centimeters uncut at the top and at the bottom. 3. Cut a white sheet of paper so that it fits in the shoebox. Place the paper in the bottom of the box so that it lies flat. 4. Fill the jar with water and set it carefully in the box. Line it up with the 2 slits. 5. Darken the room. Then shine the torch through the 2 slits in the box. 2 beams of light come through the slits in the box. Look and discover. Does each ray continue in a straight line inside the jar? Where do the light rays first change direction? Do the rays bend again as they leave the jar? Light passes through different substances at different speeds. When the light rays go from air into water, they slow down and refract, or change direction. The rays bend again as they leave the jar. The light is very bright where the rays cross. Making a rainbow. White light, including sunlight, is actually made up of a rainbow of colored light. Create your own rainbow to see for yourself. Materials. A shallow glass baking dish. A hand mirror. Modeling clay. Water. A torch. A large sheet of white cardboard. A prism separates white light into different wavelengths, so all the colors of the visible spectrum can be seen. Rainbows. Why do you sometimes see a rainbow during a rain shower? Raindrops act like tiny prisms. Light with longer wavelengths, such as red, is refracted less than light with shorter wavelengths, such as blue. As sunlight is refracted, the colors that make up the light are separated. Procedure. 1. Place the mirror in the dish at an angle of about 45 degrees. Use modeling clay to secure it so it does not slip. Fill the dish halfway with water. 2. Shine the torch onto the section of the mirror that is under the water. A rainbow appears on the cardboard. 3. Hold the cardboard at an angle above the dish to catch the reflection of the light. Move the torch slightly for a better image. Look and discover. What colors make up white light? White light is made up of different colors of light, each with its own wavelength. The range of colors, from red to violet, is called the visible spectrum. Some materials, such as glass, water, and objects such as prisms, refract white light in such way that the light separates into the colors of the visible spectrum. In this activity, the water produced a visible spectrum or rainbow. Optical technology. The study of light and its behavior has led to the development of many inventions, such as the camera and the spectroscope. The activities in this chapter will enable you to create simple versions of some of these inventions. Making a pinhole camera. You can make a simple camera to show how an image can be formed on a screen. The screen represents the film used in a camera to record the image. Ask an adult to help you with steps I and 2. Materials. A shoebox with lid. Matte black paper. Glue. A pencil. A ruler. Scissors. Tracing paper. Double-sided tape. A drawing compass. An 8 cm square of aluminium foil. A pin. Procedure. 1. Line the inside of the shoebox with black paper. At one short end, cut out a square, leaving a 2.5 cm frame. Cut tracing paper to fit over the frame and tape it in place. 2. Use the compass to draw a circle 3.25 cm in diameter at the opposite end of the box. Cut out the circle and tape foil over the hole. Poke a tiny hole in its center with a pin. Put the lid on the box. 3. Stand by an open window in a darkened room. Point the pinhole at an object outside, such as a tree. Observe the image of the object on the tracing paper screen. Look and discover. What did you see on the tracing paper? Some of the light reflecting from the object passes through the pinhole and hits the screen. An image of the object is formed on the screen. The light beams cross as they pass through the pinhole. Light from the top of the object strikes the bottom of the screen, and light from the bottom of the object strikes the top of the screen. This makes the image on the screen appear upside down. How a box camera works. Light passes through the lens of a single-lens reflex camera and is reflected by a mirror inside the camera onto a screen upside down. A prism in the camera sends light from the reflection out of the viewfinder to your eye right side up. When you take the photograph, the mirror flips upwards so that the light reaches the film. William Fox Talbot made this box. Camera in 1835. Image reflected upside down on screen. Lens. Making a periscope. A periscope is an instrument used to view objects that may be hidden by an obstacle. Periscopes can be used to look around corners. In this activity, you can make a simple periscope. Ask an adult to help you with steps 2, 3, and 5. Materials. A cardboard milk or juice carton. A triangular piece of cardboard. A pen. Scissors. 2 small mirrors. A pencil. Procedure. 1. Use the triangular piece of cardboard to help you draw 2 diagonal lines on one side of the cardboard carton. 2. Cut a slit along each line. The slits should be just wide enough to hold the mirrors firmly. 3. Draw 2 lines on the side of the carton directly opposite the first slits. Cut slits as before. 4. Push the mirrors through the slits. Put the top mirror shiny side down and the lower mirror shiny side up. 5. Draw a large square on the carton in front of the top mirror. Carefully cut out the square. 6. Use a pencil to make a small hole in the back of the carton, level with the bottom mirror. 7. Point the large square hole towards an object and look into the small hole to see around corners. Look and discover. What did you see when you looked through your periscope? How does a periscope work? The object in front of the large square hole was visible when viewed through the periscope. In a simple periscope, light reflected from the object enters the square hole and strikes the top mirror. The top mirror reflects an image of the object to the bottom mirror, which reflects the image through the small hole to the observer's eye. More complex periscopes also use lenses to magnify the image. Making spectroscope. A spectroscope is an instrument that creates a spectrum from a beam of light. It allows you to see all of the colors that make up that beam of light. In this activity, you will make a simple spectroscope and view the spectrums produced by a candle and by a glowing light bulb. Ask an adult to help you with steps 1 and 2. Materials. Thick cardboard. A ruler. A pencil. Scissors. Tape. A large sheet of white cardboard. A candle and holder. A prism. A sheet of dark paper. A magnifying glass. A lamp with no shade. Procedure. 1. Cut out a 15 cm by 2.5 cm strip from the thick cardboard, cutting from the middle of one of the edges. Cover most of the missing section with dark paper, leaving only a 1.5 mm slit uncovered along its length. Tape the dark paper in place. Darken the room. 2. Tape the cardboard to your table with the slit at the bottom. Place the white cardboard about 50 centimeters away to act as a screen. Ask an adult to light the candle and place it behind the slit. Then have the adult or a friend hold a magnifying glass between the slit and the screen, moving it back and forth to focus the image of the light onto the screen. If necessary, adjust the angle of the screen. 3. Hold the prism between the magnifying glass and the screen. Rotate the prism until you see a spectrum. If the spectrum on the screen is too dim to show the colors clearly, try looking at the light source through the prism and moving it back and forth until you see the spectrum properly. 4. Read the exploring spectrums portion of the activity. Predict whether the spectrum produced by a glowing light bulb will be similar to or different from the spectrum produced by a burning candle. Repeat the experiment using the light bulb as a light source. Look and discover. When you looked at the spectrum produced by light from the candle, how many colors could you see? Was the spectrum continuous, with no separate bright lines present? How did this spectrum compare with the one produced by light from a bulb? Light from each source passed through the small slit, and the image of the slit was focused on the screen by the magnifying glass. When they passed through the prism, the light rays were separated into a spectrum. Both light sources are incandescent, and each should therefore produce a continuous spectrum. Exploring spectrums. Different light sources produce different spectrums. An incandescent light source, one that is produced by heat energy, has a continuous spectrum in which all visible colors are present. Some gases produce a spectrum with a few brightly colored lines. Sodium gas, which is often used in street lights, produces a spectrum with a bright yellow line. Continuous spectrum. Bright line spectrum of sodium gas. Sunlight. Today we know that Earth rotates on its axis and revolves around the Sun. However, when the Polish astronomer Nicholas Copernicus proposed this theory in the 1500s, most people refused to believe it. They were convinced that Earth was at the center of the universe. Luckily, a few bold thinkers, including Galileo Galilei, saw the wisdom of Copernicus's theory. As you do the activities in this chapter, you will follow in the footsteps of those early scientists who drew their conclusions based on careful observations. Day and night. What causes day and night? Investigate with the following activity. Ask an adult to help you with step I. Materials. A plastic foam ball. A thin wooden skewer about 25 centimeters long. A felt tip pen. Modeling clay. A desk lamp. Procedure. 1. Ask an adult to help you carefully push the wooden skewer through the center of the plastic foam ball. Use a felt tip pen to make a line of large dots around the middle of the ball, as shown above. 2. Secure one end of the skewer in the modeling clay. Tilt the skewer so that it is at a slight angle. This represents the tilt of Earth's axis. 3. Darken the room and turn on the lamp. Slowly rotate the skewer so that the dots on the ball move in and out of the light. Look and discover. What happened when you rotated the ball? How much of the ball did the light shine on at one time? How many dots were in the light at one time? Like the ball on the skewer, Earth rotates on an invisible, tilted axis as it revolves around the sun. When the ball spins, different sides move into and out of the light. Earth does the same on its axis. One side of it faces the sun as the other side faces away. This means that when it is day in some parts of the world, it is night in others. The changing seasons. This simple activity can show you how the seasons change as Earth, rotating on its tilted axis, travels around the sun. You will be able to see how the length of daylight and nighttime change according to the season. Materials. A lamp with no shade. Masking tape. A pen. A globe on a stand. Modeling clay. Procedure. 1. Place the lamp on a table. Use pieces of the masking tape and a pen to mark 4 positions around the lamp at right angles to each other and about 1 meter from the lamp. Label the tape pieces March, June, September, and December. 2. Place the globe at the December position. Put books underneath it until its top is level with the top of the lamp bulb. Fasten small balls of clay to the globe at the equator, the North Pole, the South Pole, halfway between the equator and the North Pole, and halfway between the equator and the South Pole. 3. Point the South Pole of the globe towards the bulb, the sun. This is approximately the position of Earth and the sun in the month of December. 4. Darken the room and turn on the lamp. Rotate the globe slowly anti-clockwise. 1 complete rotation represents 24 hours. When the clay is lit by the lamp, that part of Earth is experiencing day. When the clay is in shadow, it is night. 5. Repeat steps 1 to 4 with the globe at the March, June, and September positions. Keep the North Pole of Earth's axis pointing in the same direction as you move the globe around the lamp. In the June position, the North Pole will tilt towards the sun. The equinoxes and the solstices. Equinoxes occur twice each year. These are the 2 days on which the sun is directly overhead at noon on the equator, and daylight hours equal darkness hours in both hemispheres. The summer and winter. Solstices are the 2 days with the longest and shortest amounts of daylight. June 21st, summer solstice in northern hemisphere, winter solstice in southern hemisphere. March 21st, equinox in both hemispheres. September 23rd, equinox in both hemispheres. December 22nd, winter solstice in northern hemisphere, summer solstice in southern hemisphere. Look and discover. When you rotated the globe in the December position, how much daylight fell on the poles? How much light did the poles get at the March, June, and September positions? How much daylight did the equator get? Because Earth's axis is tilted, parts of Earth receive more daylight at different times of the year, and the sun's rays hit different parts of Earth at different angles. This causes the varying lengths of day and night and the change in seasons. Making a sundial. We can use the position of the sun in the sky to help tell us what time it is. The following activity will help you make a clock called a sundial to tell the time on sunny days. Remember that it is dangerous to look directly at the sun. Use the angle of shadows to tell time. Ask an adult to help you with step 2. Materials. A piece of cardboard. A drawing compass. Scissors. A flower pot. A sharp pencil. Modeling clay. Glue. Procedure. 1. Draw a large circle on the cardboard, using the compass. 2. Cut out the circle and make a small hole in the center. 3. Push the point of the pencil through the hole in the bottom of the flower pot. Use the clay to hold the pencil in place. 4. Turn the pot over so that the pencil is protruding. Put the cardboard circle over the pencil and glue it to the bottom of the flower pot. 5. Stand the flower pot outside on a sunny morning. Every hour on the hour, draw around the shadow of the pencil on the card. Write the time next to each mark. Don't move the sundial. 6. Look at the sundial again on the next sunny day. Make sure it has not moved from its position. If it rains before the next sunny day, cover the sundial loosely with plastic. Look and discover. When you looked at the sundial again, did the pencil's shadow point to the correct time? Explain what happened. The rotation of Earth on its axis makes the sun appear to move across the sky from east to west every day. The shadows cast by the sun also appear to move. On sunny days, these shadows can be used to tell time, since the shadows will be cast in almost the same position at the same time each day. Shadows. When light strikes an opaque object, the light is blocked, creating a shadow. Most shadows are made up of a darker area and a lighter area. The darker area of a shadow, where all the light is blocked, is called the umbra. The lighter part is called the penumbra. In this area, only part of the light is blocked. With the light behind him and low in the sky, this boy casts a long shadow. The moon. Reflected sunlight gives the moon its brightness. The same side of the moon is always facing Earth. This is because the moon rotates only once during its month-long orbit around Earth. Though the far side of the moon is sometimes called the dark side, it is not always dark. It experiences sunshine and darkness, just as the near side of the moon does, we just cannot see that from Earth. The activities in this chapter will help you explore how the moon's motion changes the way it looks to us. The moon's phases. Complete this activity with a friend to see how the moon appears from Earth. You can also visualize how Earth and the moon appear from space. Ask an adult to help you with step 1. Materials. A pencil. A tennis ball. A pen. A desk lamp. Procedure. 1. Make a hole in the tennis ball with a sharp object. You may need an adult to help you with this task. The ball will be your moon. Insert a pencil into the hole. Mark one side of the ball with an X and the other with a dark spot. 2. Turn off any overhead lights and turn on the lamp. Stand in front of the lamp, holding the tennis ball with the dark spot facing you. You will be on Earth. Have a friend stand nearby. Your friend will observe you from space. 3. Keep the tennis ball out in front of you while you slowly turn around in a circle, making sure that your body does not block light from the lamp. Look at the ball as you turn. Look and discover. As you rotated slowly, how much of the ball could you see? How did the ball's appearance change? What did your friend see? The moon circles Earth about once a month. As it moves, its phase changes. The phase is the amount of the lit part of the moon's surface that can be seen from Earth. As you slowly turn, you will see phases of the moon. As you turned, you viewed the moon as it looks from Earth. Your friend viewed how Earth and the moon look from space. A lunar month. The period from one new moon to the next is known as a lunar month. Many ancient cultures used the lunar month as a basis for their calendars, as do some cultures today. However, 12 lunar months do not make a full year. So, as time passes, important holidays based on a lunar calendar can change dates. A lunar eclipse. 2 or 3 times a year, a strange sight appears in the night sky. The moon is wholly or partly covered by a shadow. This is called a lunar eclipse. An almanac can tell you when a lunar eclipse is due. In the meantime, you can create your own lunar eclipse. Ask an adult to help you with step 1. Materials. 2 thin wooden skewers, each about 25 centimeters long. A foam ball 8 centimeters in diameter. A foam ball 4 centimeters in diameter. Modeling clay. A 10 centimeters x 60 centimeters sheet of cardboard. A desk lamp. Procedure. 1. Push a skewer into each ball. Use the clay to stand the skewers up at either end of the cardboard. Make the centers of the balls the same height. The large ball represents Earth, and the small ball represents the moon. 2. Position the lamp, which represents the sun, at the same height as Earth, but on the opposite side of Earth from the moon. Shine the light directly at Earth. Then move the cardboard a small amount from side to side. Earth blocks light from the sun, casting a shadow over the moon. Look and discover. What happened to the moon when you moved the cardboard? Where did Earth cast a shadow? Lunar eclipses occur when the moon is in Earth's shadow. This happens when Earth sits exactly between the sun and the moon. The movement of the cardboard shows how the moon moves into Earth's shadow and out again. Lunar eclipse. Lunar eclipses occur only during a full moon. During a total lunar eclipse, the entire moon passes through Earth's shadow. It may disappear from view or be visible as a reddish disk. A partial eclipse occurs when only part of the moon passes through Earth's shadow. Conclusion. Light plays an important role in the lives of all living things. Through these activities, you have explored the different ways light behaves, inventions created to study or use light, and how light influences day and night, the seasons, and the brightness of the moon. Continue to explore and experiment with light. Discover all the exciting ways that light affects the world you live in. Glossary. Axis. The imaginary line through the center of Earth, around which Earth rotates. Equinoxes. The 2 days of the year when the sun is directly overhead at the equator at noon, and day and night are equal in length. Incandescent. Emitting light as a result of being heated. Light rays. Straight beams of light. Lunar eclipse. A time when Earth is directly between the sun and the moon, and part or all of the moon passes partially or totally into Earth's shadow. Opaque. Not letting light pass through. Orbit. The motion of one object in space around another, such as Earth around the sun or the moon around Earth. Periscope. An instrument used to view objects that may be hidden by an obstacle. Phase. The lit part of the moon's surface that can be seen from Earth. Prisms. Triangular blocks of glass or transparent plastic used to refract light. Reflection. The bouncing of light waves from a surface. Refraction. The change in direction of light rays as they pass from one medium into another. Shadow. Area of darkness produced when light is blocked by an opaque object. Single lens reflex camera. A camera in which a single lens serves as the film and the viewfinder. Solstices. The 2 days in a year when the sun is furthest from the equator at noon. Spectroscope. An instrument that separates a beam of light into a spectrum showing all the different colors that the light contains. Sundial. An instrument that uses a shadow to indicate time of day. Translucent. Allowing some light to pass through, scattering rays in the process. Transparent. Allowing most light to pass through without scattering it. Visible spectrum. The range of colors produced by all wavelengths in white light. Wavelength. The distance from one crest to the next crest in a wave. For visible light, different wavelengths correspond to different colors.